so this is our video lesson for section 13.2. Alright, so we already started talking about gases in 13.1, and so now in 13.2 we're going to talk a little bit about liquids. Alright, so the high kinetic energy in gases and liquids allows the particles to flow past one another. Remember, in a solid, the particles, they are moving, but they're vibrating in their fixed locations. They aren't allowed to actually move past one another in a solid. Okay, that's how it retains its shape. In liquids and gases, however, those particles, they're allowed to trade places and move around each other. And so that allows them to flow. Like when you pour water, it flows over each other because those particles can trade places. So anything that can flow is called a fluid. Now, a lot of times if I say, what's a fluid? Everyone would tell me it's a liquid, which is true. Liquids are fluids, but they forget the other type of fluid. A gas is also a fluid. Gases can flow too. Okay, if a gas couldn't flow, turning on the air conditioning wouldn't do anything because then air wouldn't flow into the room. So anything that can flow is called a fluid. So that includes liquids and gases. All right, so intermolecular forces keep the particles in a liquid close together, which is why liquids have a definite volume unlike gases. All right, so remember, we talked about intermolecular forces before. We have, London dispersion, dipole-dipole hydrogen bonding. So those forces, remember, they act kind of like little magnets. They kind of hold the particles close together. So see how close they are in this picture? So even though they can move past one another, in a liquid, they're still really close. That's why you can't really compress a liquid because the particles are already just very close together. And so even though they can move past one another and change shape, they don't actually change volume like gases, which we talked about yesterday. Those are compressible. All right, so let's click. All right, so when a liquid converts into a gas and it's not boiling, so we have not reached the boiling point, it is referred to as evaporation. So for example, if I left out a glass of water on my counter and day after day after day I just left it there, eventually I'd slowly be able to see the level of the water falling, and eventually the glass would be completely empty. I didn't heat it, so it wasn't boiling, so that's evaporation. All right, during evaporation, only the molecules with the highest kinetic energy can escape the surface of the liquid. So remember, we've discussed that every particle in a sample does not have the same kinetic energy. It's a range, just like when y'all take a test in my class. You don't all make the same grade. There's a range of grades you make, okay? So the fastest particles, the ones with the most kinetic energy, get to leave and become a gas. It's kind of like if y'all took a placement test. The ones of you that made the highest would be able to pass on to the next class, and the ones that made the lower grade would stay in this class. Okay, so the fastest particles get to escape and become a gas. And so that leaves who? Well, it leaves the lower kinetic energy particles, or the slower ones. So remember, temperature is based on the speed of the particles. So if the fast ones leave, those are the ones that have the highest temperature. So when you have the slow ones left, those are the ones with the lower temperature. And so it results in a lower temperature. So you might think, well, if I leave a glass of water out evaporating, why didn't it eventually turn into ice? Or why doesn't it get really cold like it was in the refrigerator if the temperature keeps lowering? Well, you have to think, what happens is when those particles evaporate and it cools the temperature down, what around it would warm it back up? The atmosphere. The atmosphere around it will warm it back up. So that's why the water doesn't continuously just get colder and colder and colder. So the reason I have this picture is that's why we sweat. Okay, when you get really hot, your body produces sweat, a liquid on our skin, and then as that liquid evaporates, it cools our skin. Okay, so that's the reason that we sweat, is because evaporation is a cooling process. That's also why if you've ever touched rubbing alcohol, it evaporates very quickly, and so when you touch it, you can feel the cold, versus for water, you can't feel it quite as much, only because we're just so used to being around water. All right, so let's click. So this next thing, vapor pressure, oh my goodness. Some people just have a lot of trouble with it, so I'm going to go over it. And of course, since this is a video, you can rewind it as many times as you need to hear it. All right, so vapor pressure is a measure of the force exerted by a gas above a liquid. An increase in temperature increases the vapor pressure produced by a liquid. Okay, so let's look at the pictures and see if we can wrap our minds around this. All right, so this right here is a flask full of bromine. Bromine is naturally a liquid, but it evaporates, and it evaporates into a brownish gas so we can actually see it. That's why I use this picture. Okay, so when you put liquid bromine in a container and you close it, then eventually it's going to start evaporating. Now with water, we can't really see that process because it's colorless, but with bromine you can. So picture when we first close it, this whole area will be colorless, just like if just regular air were in there. And then over time, you'd start seeing a little bit of brown, and then as time passes, it'd get a little bit darker and a little bit darker. Now, it can't fully evaporate, of course, because we have it closed. So eventually, no more would be able to evaporate. That's when it's called saturated. So you have your liquid down here at the bottom. You have your gas up here at the top. The pressure produced by this gas above this liquid is called the vapor pressure. Because remember, a vapor is a substance that is normally a solid or liquid that has turned into a gas. So that's why we call it a vapor. Okay, so over here is just another picture of the same thing. This one we have a little bit of water in the bottom. And so those particles that evaporate and become a gas, those are what exert the vapor pressure. Okay, for vapor pressure of a liquid, for some of the things that we talk about, it kind of helps if you think of it as the force of the liquid particles pressing out to become a gas. That can kind of help a little bit. So if you think of it as the force of the liquid particles trying to leave, that can help a little bit. So as temperature increases, vapor pressure increases. Well, why would that happen? Well, remember, the particles with the highest kinetic energy are the ones that can evaporate. Well, if we increase the temperature, wouldn't more particles have high kinetic energy? Yes. So then more particles could evaporate. And of course, the more particles you have, the more pressure, because pressure is based on collisions of particles. So the more particles you have, the more they collide with each other. All right, you get that gas built up, that vapor, and then that's more vapor pressure. All right, so let's click and look at boiling point. All right, so the rate of evaporation increases as temperature increases. And we just discussed that because, remember, the particles with the highest kinetic energy evaporate. So if we can increase temperature, more of those particles would have enough kinetic energy to evaporate. When a liquid is heated to a temperature at which all the particles have enough kinetic energy to vaporize, that's when it's at its boiling point. Okay, so remember, evaporation, it happens only at the surface. And the really, really fast, high kinetic energy particles can escape the surface. That's why you can't see evaporation happening. You can see when a liquid's boiling. You see all these bubbles. But evaporation just happens at the surface, so you don't really see anything. Now, once you heat it to where all of them have it, that's when you see all those bubbles forming. And if you ever really, really, really watch a pot or something like that of boiling water, you'll notice that the bubbles just come from everywhere. Sometimes they come from the sides of the container. Sometimes they come from the bottom. Every now and then you'll see one just randomly come out of the middle of the liquid. And that's just because they all have the ability to vaporize at that point. So, what is the definition of boiling point? Because I'm pretty sure you've been taught one, but it's not the one we use in here. Alright, so a lot of people, if I said, what's boiling point? You would tell me, oh, it's the temperature at which something boils. Or if I'm lucky, you'll say, it's the temperature at which something goes from liquid to a gas. But that's not the definition. Technical definition of boiling point is the temperature at which the vapor pressure of the liquid is equal to the external pressure that's on the liquid. And that's the boiling point. Okay, so vapor pressure equals external pressure. So remember how I just told you, for vapor pressure, think of it as the force of the liquid trying to come out. Well, external pressure is the air pushing down. So in other words, we have two opposing forces here. The liquid's trying to evaporate out, so it's coming up. But the air is like, stay down there. It's pressing down. So in other words, you have these two forces going against each other. Now, before the liquid is boiling, every time it tries to come up, that air pressure pushes it right back down because it's greater. So it tries to come up, external pressure pushes it back down. But eventually, once those two are equal, and it tries to hit it back down, because they're equal at that point, it can't do anything. It's not stronger anymore. And so then those particles can just come out as they please. Okay, so I know it's confusing because you may thought you already knew what boiling point was, but as with many things in this class, sorry. This is the technical definitions, that's what we have to go with. Alright, so remember, it's when vapor pressure, the pressure of the liquid coming out to become a gas, equals the air pressure pressing down on it. We say external pressure because, of course, it could be in a vacuum or something like that, so we don't always know what that external pressure is going to be. So, if boiling point is based on external pressure, if we change external pressure, could we change boiling point? The answer is yes, we can. Okay, well, how can we change external pressure? Well, there's many ways. You could artificially do it in the lab by putting something in a vacuum or something like that. Or you could just go to a different altitude. Okay, as you go to different altitudes, the air pressure changes because you don't have as much air pressing down on you at the top of the mountain as we do down here at sea level. Okay, so down here at sea level, let's just pretend we have this much. If you climb up a mountain, then you only have this much. So that's less air pressing down on you. So because atmospheric pressure is lower at higher altitudes, so you climb up the mountain, so external pressure goes down, that means the boiling point goes down because the liquid does not have to get as hot to fight that atmospheric pressure and boil. So if you ever look at like things like, you know, cake mix boxes or something like that, a lot of times they'll have special high altitude cooking directions because sometimes you have to change things because of the fact that everything is at a different boiling point at that point. All right, on the other hand, if we could increase external pressure and make it push harder down, it would be harder to boil that liquid and the boiling point would increase. This is what happens with pressure cookers. Now, pressure cookers and crock pots aren't the same thing. Okay, a pressure cooker has a lid that actually locks in place. And so since it doesn't allow any of the steam to escape, it builds up pressure inside. And so again, as that pressure builds up, it keeps forcing that liquid to stay a liquid. It won't let it come up and become a gas. So we have to heat it up a lot more to get it to boil. And so if you cook food at a higher temperature, then it cooks faster. So pressure cookers a lot of times are used for rice because rice is known to kind of take a while. And you can help speed that process up. So remember, boiling point is based on when vapor pressure equals external pressure. So if we can change external pressure, we can change the boiling point. So let's look at this section assessment here. So in terms of kinetic energy, explain how a molecule in a liquid evaporates. All right, so remember, we have a wide range of kinetic energies in a sample. So who leaves first? The fastest ones. So we could say, since we have to do it in terms of kinetic energy, the particles with the most kinetic energy evaporate from the surface. That's all you would need to write there. Okay, the particles with the most kinetic energy would evaporate first from the surface. Okay? So let's look at number 2, because obviously you can rewind this at any point in time if you didn't get all that. Alright, so let's look at number 2. Explain why the boiling point of a liquid varies with atmospheric pressure. Well, what is boiling point? Boiling point is when vapor pressure equals external pressure. In our case, most of the time, our external pressure is the atmosphere. That's what's outside of us. Okay? So, if boiling point is vapor pressure equaling external pressure or atmospheric pressure, if this changes, then boiling point changes. So that's how you have to write. Boiling point is when vapor pressure equals external pressure. So if external pressure changes, then boiling point changes. Alright, so let's look at the third one. So explain how evaporation lowers the temperature of a liquid. Well, like in number 1, we already said who evaporates. Who evaporates first? The fastest particles evaporate first, which leaves who? So the slower ones are left behind. And remember, y'all, temperature is based on kinetic energy. So slower particles have lower temperature, and that's how temperature is lowered. So you can say the fast particles evaporate first, leaving the slow ones, which have a lower temperature. That's all you have to say. All right? So that's liquids right there for you. Okay? Make sure you know definition of boiling point. That's a commonly confused thing. And about this evaporation being a cooling process. But otherwise, that's it.